Okay, so I don't really need an introduction. I'm Joan Fuller. I'll give you one anyway. So a little bit about this program. It started as in 2007 as part of Air Force Research Lab's Focused Long-Term Challenge sort of workshop that we had down in Williamsburg, Virginia. And a group of program managers and lab researchers sort of self-coalesced around some basic research topics that looked like they needed a little bit of effort or a little bit of emphasis effort here at AFOSR. And this one really had the champion of Dr. Alan Garskattan, who was the chief scientist of the Propulsion Directorate, who's since retired, John Schmischer, Doug Smith's predecessor, Rhett Jeffries, Kit Reinhardt, and others really helped to put in words what many in the lab were articulating, is that thermal scaling phenomena was now becoming apparent as we went to smaller and smaller systems and faster systems. And so I kind of sort of inherited this program because everybody else was too busy. And so for the first 6 months with the lab help, I really tried to put together a cohesive program. And at the time, I thought I would actually keep it, and unfortunately, I got moved on to other things. And so this program, this portfolio, has really been managed by 4 other people and never me. So this is the first time that I'm actually taking ownership of what I put together in 2007. But everything that's in the portfolio is really created by Joni Arnold, Dr. Arnold in RX, and Kumar Jada, who I had on loan from RX. And I think they've done an excellent job of identifying the space where the basic science really needs to be focused to address Air Force applications for future systems. So this is the pretty slide. It sort of captures everything. You can kind of put it in your pocket and take it with you. The motivation of this portfolio is to really exploit phonons. And so you've heard a lot this week about photons. You've heard a little bit about electrons. If you were here for Dr. Kirchik's talk, you heard about bosons and fermions. Phonons are a little bit strange because we all think we understand heat. Turns out we don't. We understand it through the Boltzmann's equations and things like that on a bulk scale, and you kind of understand how heat transfers through media and how it doesn't. But as we get to smaller and smaller scales in which the mean free path is on the same order as the structure is, and I'm talking in the order of 1 to 5 nanometers, pretty much all of our theories fail. And so our ability to really control phonons and to manipulate them and to optimize them for everything from new devices all the way to thermal management of our current systems is really hinging on our ability to understand what the phonon is doing when it sees the interface. If it's in an oxide system or an insulating system, it's all phonon-phonon. Unfortunately, most of the things we work with are heterogeneous. It's an oxide on a metallic. So you have the effect of electrons in the system, and so you now have phonon-electron coupling. And if you have external fields applied, you have the additional complication of now trying to sort out all the different modes and what the phonon is doing and which part is dominant. So there's a community that's sort of growing around this area of phononics, this ability to manipulate phonons. Very analogous to what Dr. Pomrinke mentioned earlier and what you didn't hear with Harold Weinstock's talk yesterday in the photonics community. Our ability to manipulate heat or phonons on a very small scale is opening up this new space which some people have called phononics. So the scientific challenges are really developing a science base to understand and control thermal transport in heterogeneous systems, and I'll keep harping on that because it's important. In exploiting these interactions between phonons, and electrons and their interactions with the surrounding material, it's kind of the theme of understanding what the phonon is doing, being able to predict what it will do depending on what you've done to it. So there's a lot of Air Force applications for understanding heat transfer in these systems. Thermal is really one of the limiting factors for Air Force systems, everything from engines to directed energy systems, and unfortunately, Dr. Riker left because I was going to make fun of him, that it turns out that in most systems, be it space or directed energy, they're incredibly hard. The directed energy system, the amount of heat it has to move away from the system so quick and so fast is probably the limiting factor forever. And so hypersonics, which you heard this morning with John Schmischer, we do spend a lot of time understanding how energy couples on the surface to disturb the boundary layer. It actually gets worse in other systems. So just one highlight, I have mentioned this before, a payoff that can come out of understanding how the phonons are interacting with the material is demonstrated by a project that is in one of my MURIs, and it was a highlight that I've presented, and it's been in Science a few years back. But it turns out if you can atomically control a layered material, in this case it was, I believe, tungsten selenium, and they actually put atomically thin layers down, they were able to get experimentally prove that you can get an order of magnitude lower thermal conductivity in designed materials than what theory would have ever predicted. The rationale for that, now they understand, is because the phonon literally gets frustrated within these structures. It has no way of propagating through the media anymore. And so the ability to realize ultra-low thermal conductivity in materials sort of opens up new ways of designing thermal management into our systems. So the portfolio looks like this. It's been relatively flat since it's been in my program. And I would just like to point out that the budget's pretty big for a portfolio, but it's very small in number of projects. There are 27 principal investigators, or 27 individual grants, fairly large grants. I tend to I prefer larger awards that are multidisciplinary and collaborative in nature. It makes it a little bit easier to manage, and I think it's more beneficial to the academic community to let them self-form and put together MURI-like efforts. I'm also fortunate to have one MURI topic that has 2 awards. This MURI was actually written in collaboration with my Army research colleague, Rob Mance, at the time, and who now is DARPA for a little while. What's really impressive about such a small number of PIs is the pedigree of these folks. Just an incredibly dynamic community of senior researchers in the physics community really mentoring the younger generation. I'm fortunate to have 8 NSF career awardees, and so I'm able to tap into some of the best people that NSF funds. One, NDSEG, this is our fellowship program that we have here, and this just really floors me. So I took over this program after Kumar left me this fall. And so around November, December timeframe, I did a data call, and I asked the PIs to send me all their publications that cited OSR in the last 3 years. And I got back 117. And so I've been trying to read through all of them. I haven't quite made it. But it's an incredibly productive community. And I wouldn't say this is unique to my portfolio, but it's quite an achievement that this, almost every journal article journal that I pick up has one of my PIs publishing his latest work. So it's quite interesting. Also means I end up reading a lot. But scientific challenges, just to give you the list, this is what the current program is focused on. A subset of the current program is what will be my focus for the next few years. And that's looking at multi-carrier interfacial transport, this coupling of electron and phonons at a heterogeneous interface. It's distinct in that we do tend to focus in the Air Force program on this multi-component carrier transport, whereas other funding agents have focused more on the single carrier. Another challenge has been realized is that when the bounding media has nanoscale dimensions, you saw this a little bit in Chad Merkin's talk, if you saw the really exquisite nanowires that he can make. But there's unusual effects that occur. It's very difficult to experimentally measure these, but also when you do manage to get an experimental data point, it doesn't match theory at all. And then when you add the 3rd level of complexity, which is the actual material, because at some point you have to make something to see a phonon. And if you look at, for example, the chalcogenides, which you heard mentioned yesterday and this morning from Dr. Wang, these are the interesting materials. These are the ones you really would like to exploit and use in systems. But unfortunately, in the germanium system, you have thermal contributions from both electrons and phonons. And so how do you sort that out? It's really quite challenging. And so it's one of the 3 challenges that I've chosen to focus on. So the portfolio is currently divided into 3 scientific focus areas. The first sub-area 1 is this nanoscale thermal transport. It's what the challenges are based around. And it's what my examples will be from today. And so the gaps that we just simply don't know, and when I say don't know, in 2006 people postulated these, and so there's more knowledge now than there was in 2006, and I imagine by the time my grants end, some of these will have fallen off. But we are starting to really focus more on interface effects. What's the lattice mismatch, atom mixing? The current models really sort of throw all that out. It's really quite complicated. And I don't think many people thought the interfaces had that much to do with thermal conductivity until about 4 years ago. There is still a pretty big discrepancy between predictions and experimental data. This is some work from one of the PIs who I wasn't obviously funding in '99, but Ken Goodson at Stanford. And this is the prediction, and you can see the experimental data is still there's a pretty big disparity in that. We still don't understand the contribution of long wavelength versus small wavelength, and how do you decouple the phonon modes? Which ones are the dominant ones at these various wavelengths? And just in general, we don't have a good feeling for thermal transport phenomena in these nanoscale dimensions. And one of the things that kind of struck me is that there is no unifying theory for thermal conductivity. You would just think there would be. I mean, something we all study in physical chemistry, and back in the 22 years ago when I had a physics class, I just assumed that we'd kind of figured out thermal conductivity. Turns out we hadn't. And so now going back and trying to apply pretty generalized theories to a very specific nanoscale or nanostructured scale is really quite challenging. The other two sub-areas, which I will not give examples from, but you have the slide packet in front of you, or if you're online, you have it online, are really very application specific. The first is heat removal for large-scale heat flux situations. Think high-power microwaves or directed energy lasers. And just the current class of heat sinks really aren't sufficient for sucking away that much heat. In addition, we don't understand what the physical mechanisms are for dissipating large quantities of heat, especially at nanostructured features. So there's a lot of room here for the material science community and for some of the systems engineering approaches to look at how do you design in better phase change materials, or just in general better ways of moving large amounts of heat very quickly without damaging the structure, or better yet, the system. So Andy Williams is one of the bright guys in the Space Vehicles Directorate. He actually has a team of folks working in this general area for both applied and basic science. And so I always point people to him because he does understand the systems integration challenges, which is really important. The third sub-area is also one of these applications driven, which is important to understand the system in which this component would live. And that's how do we tackle these irregular or these massive thermal transients. And you see this in terms of like thermoelectrics, and it's a very popular topic. But engineering these structures, and this is a PI that's actually one of Ollie's former postdocs, who I will not try to pronounce Alp's last name, but really trying to, there's a lot of science still left to be done in the thermoelectric community. But I think one of the big challenges that you see in this is the reality of the material really needs to be addressed in a systems engineering focused way. So you can't actually just do theory for theory's sake in the case of thermal storage and conversion. So that kind of leads me to my program trends. I think theory is at the root of all of the hard problems. It kind of leads to the applications. The more we understand, the more we can manipulate, the more we can exploit phonons for our own use. And if we can't exploit them for good, then we should at least mitigate their bad. Heat removal, as these projects wind down, they will just wind down. And I just want to point out, thermal storage and conversion is a very well-funded area now by ARPA-E. If you do a Google on their latest announcement of awards, you will see a pretty large chunk of money, in the tens of millions of dollars, specifically addressing thermal storage and conversion. So I feel comfortable in an active watch mode for the next couple of years. And because of that, I've given a lot of thought the last 2 months to really rebranding this portfolio. It is, its genesis is in the the fluids community or the combustion community. the problem is that if you Google thermal science, and trust me, I did, you get a really nice journal on combustion, which has nothing to do with phonons. And if you really focus, if you leave the word thermal science in there, I either get white papers from the combustion community or from the thermal storage and conversion community. And if you look at the actual people, they're either in physics portfolios and primarily funded by the condensed matter physics community or the solid state physics community. So I'm seriously thinking about changing the name. I will talk to the PIs first. But this program really is a physics-based portfolio, not a material science program. So there are a fair amount of other funding agencies that work in related areas. I put the DOE laundry list because DOE is the major player, second only to NSF. I do have some interactions with my NSF counterparts. Dan Finatello actually just funded a career award from someone at Cornell who would actually fit very nicely in my portfolio. DARPA focuses mainly on thermal management technologies, as you might expect. ONR has a really nice program. It's actually, I ripped off most of their PIs when I got my MURI started back in 2007. Mark Spector is the program officer, and he does a very, very good job of thermal management and looking at the science to actually accelerate thermal management techniques. So really very nice work there. ARO has a pretty nice program as well. Rob Mance was the person I worked with, but David Stepp also has some very interesting property characterization. And then ARPA-E, clearly the big dog, and one of the major players for industrial and consumer-related large-scale storage issues, and funding some of really exciting work. So what's the current state of the art in that first focus area, the one that I'm interested in primarily? And that is that, so if you go back and you look at, what do we know? Well, we know what we know comes from 1959, acoustic mismatch theory. This gives you sort of the boundaries for which a phonon would move. And so acoustic mismatch theory is basically saying that when a phonon sees an interface, it goes straight through. It's like it's not even there. So they call that ballistic transport. The second model, diffuse mismatch theory, is a little bit younger, basically says that when a phonon sees this interface, it's diffusively scattered, and so it's a little bit slower. So in reality, these two models, these two theories, sort of predict the upper and lower bounds for what a phonon might be expected to do. But again, these theories are based in bulk properties, not nano properties. So in reality, there's both numerical and experimental show, especially in these low aspect ratio and thin films, is that phonons undergo anomalous dispersion. It's some hybrid, and it really depends on what the nanostructure is that it's interacting with. And so it's really, you have to account for the interface just as much as you account for the phonon modes in these systems to be able to understand or be able to have a predictive thermal conductivity model. So I'll give you a couple examples. I won't spend a lot of time on this. I have talking points and I have papers if you're really interested. But I figure it's late in the day and this is all computational or model-based work. But what I wanted to point out is how people are approaching this and sort of the techniques that they're trying to use, leveraging what has been done in other communities. And so this is a young investigator, Alan McGahey, is at Carnegie Mellon, and he's looking at thermal conductivity from first principles. And what's interesting about that is that his goal would be to do bottoms-up thermal prediction. So if you know the geometry of your nanostructure a priori, could you in turn then turn around and find out what the thermal conductivity of that nanostructure would be? There's a lot of multi-physics challenges in that. I just put the equation up there to prove to people that I actually know what an equation is. But you really do need to look at this term here, this anamorphic term, which is where the phonon properties actually come from. And so his data is, this is a paper that just came out. I'd be happy to give anybody a copy of it if they would like. But it's the January issue of Applied Physics Letters. And so his inputs to his model are he knows what the geometry is. He knows what the bulk phonon frequencies are. Those are measured from spectral properties. He knows what the group velocities are. And he doesn't know what the mean free paths are. By the way, there's some really nice work from Gang Chen at MIT looking at mean free paths. So there's a nice synergy in the community of collecting this data for model systems where the structure is very well defined. And so he's able to, with some interesting Monte Carlo samplings of the free paths of either it's phonon-phonon or phonon boundary scattering, able to predict that in this particular structure, this is a silicon-based structure, that the conductivity is approaching bulk conductivity a little bit faster than you might expect from what's the Matheson rule, which is the traditional way of predicting thermal conductivity. And so here's the nice plot showing that yes, his data is the solid lines either through plane or excuse me, in plane or through plane. So it's kind of close, but it's not. I think the challenge is because he's not taking into effect the quantum effects. I think this is a good first step. And the last part of the paper, he actually does mention that one of the goals is to have a guide, not necessarily a rule. So to have a tool or a model that helps you to sort of predict or at least help you in designing a new material. And you can think metamaterials if that helps, but designing a new structure that would perhaps give you a desirable conductivity, this is still much, much better than we've had so far. It needs experimental data, though, to validate if the model actually holds for complex geometries. So that was a simple phonon-phonon. The next hard challenge is phonon-electrons. And my little simple diagram is the metal here and the non-metal here. You've got the coupling of electrons, phonons here, and only phonons on the non-metal side. And this phonon trap, this spot where the phonon has a choice of what to do and tends to get stuck here and resistance goes up. And that's where the heat buildup occurs in these materials. So the real challenge in understanding this is the models don't hold at all. The models are either meant only for metals or only for nonmetallics. And there simply aren't any interatomic potentials for some of these systems. So this is a carbon nanotube metal interface. And in his molecular dynamic simulation, he's actually has tried to to model what experimental data shows for these particular systems. And Goodson and Fisher are both in the program. And you can see the experimental data is off the plot for both of them. But Ruan's work is way down here. And this is interface thermal resistance increasing as the carbon nanotube volume fraction increases going this way. So there's still a lot of work to be done here. This is his first data coming out of the project. And there's some hope, I think, that if he incorporates the defects at the interface, of pressure effects and some of the quantum effects of actually how do they couple at the interface and especially at the defects, the model will predict. But this is just to point out that this is a really hard problem. People have been working on it now for about 10 years. It will not easily be solved. So the next challenge is to scale this up. And you'll hear a very nice talk tomorrow from Joycelyn Harrison in which she's designing these very beautiful three-dimensional hierarchical structures of carbon nanotubes. And this is very popular. I think it's a very timely thing in the academic community to be able to use some of the nanotechnologies, the nano fabrication technologies to make these complicated geometries, not just bundles and chunks of nano stuff and composites anymore, but actually to engineer structures. But if you can actually do that, if you can make a truss-like structure out of nanotubes, then in theory, and you know how to do it, you could perhaps get phonons to go the way you want them to go. But to do that, you really actually have to have a mesoscopic model that's capable of looking at propagation of phonons through complex structures, not just interfaces. So that third dimension. So this is some work being done down at UVA. Leonard Zigagli. His co-PI on this is Pam Norris, who I don't know if she was able to join us, but she was going to drive up and torture me. But I was afraid to present her work, so I presented his work. But this project is just getting started this past year, and I think we should be able to see some transfer of what we learned in this program directly to our low-density materials portfolio in the next couple of years. So all of this is possible, all of the theory and the models that are being developed because of characterization techniques. And Rick Parra gave a phenomenal talk about how lasers are really opening up experimental spaces for some of these small-scale devices. And the PI that I work with is Paul Evans. He's at Wisconsin, and he works with Martin Holt at Argonne. And back in 2006, some work on these are 2 nanometer silicon wires. It was theoretically predicted that bulk would give you 2 modes, 2 low-frequency boundary modes. But in a nanowire, all of these other frequency modes were theorized. And so this would be energy in these systems that you would not expect, but it's just because of their scale. And so the question was, how would we actually characterize that? How would we measure these different phonon modes? And it's kind of interesting if you start reading the literature. Zone boundary phonons require these large momentum transfers. It takes a lot of energy to measure these things. Visible phonons simply don't have enough. Photons simply don't have enough momentum, and so you're starting to look, in the X-ray range. X-ray and neutron scattering tend to require large volumes, which is kind of the opposite of what I have. I have small things, very small volumes. And so some recent work has been coming out in thermal diffuse X-ray scattering, and if you're an X-ray crystallographer, you had one probably week-long tutorial on this, and then you forgot about it because it took forever to do these measurements because the sources were so weak and the CC detectors didn't exist back 22 years ago. But so now with the advent of new powerful sources and some of the techniques that Rick Para mentioned, we're able to actually go back and look at thermal diffuse X-ray scattering to measure phonons. And what's cool about this technique, what used to take 2 weeks now takes 20 minutes, and you're able to get all of the data, all of the experimental data that a phonon would have. So it tells you the frequency, its amplitude, its mode. Really quite exciting. And it's not limited to a material specific. So I'm not limited to just oxides or just metallic systems. I can look at single grains if I wish. All of the modes, all the phonon modes in a single grain. So this is the first proof that this is possible. This is a silica film, 200 thick micron, and you can see this is to tell you what the phonon, where they are. And then an 80 nanometer thick film, again, you can see the emergence of new modes. So quite exciting, and I think this will sort of propel some of the model development, understanding exactly which modes are contributing in these systems. So it's kind of interesting, one of the questions is transfer. Where does the tech transfer go, or where does the science transfer to? And I always read in the airport when I'm traveling, and I didn't even know there was something called Homeland Security Newswire, but there is. So Homeland Security Newswire a few years ago had an article, and the title of it, which caught my eye when I picked it up, was Shape of Things to Come, Phononic Computer Processes Information with Heat. And I thought, well, that's just hokey. And so, you read a little bit further, and I actually brought it home and read it. And I decided to go dig up the Physics World article that it cited, and it was my PI. So this is Dr. Boan Lee. He's at the University of Singapore. Tammy Lowe is now his program manager at AORD. But he'd been funded by AORD back in 2006, and he really is the leader in being the visioneer for what is possible in the field of phononics. And so this is the article that actually Homeland Security Newswire picked up. And in this article, he had actually experimentally shown that you can have a thermal logic gate. And it's actually quite fascinating. In this colloquium series that just came out in December of 2011, which I also have a copy of if you'd like to read, called Phononics Coming to Life, he's completely mapped out the computer architecture in heat, in a thermal. So he has the logic gates, he has the thermal memory, all by numerical simulation and theoretical analysis. Experiments are a little bit behind because in some cases there just isn't enough theory to guide the experiment on what type of nanostructure you would need to get some of these effects. So this area has received enormous interest. I imagine that I will not be able to keep up with the literature. Boan Lee is very charismatic and is invited to speak at a lot of different locations and places. And so you're going to hear a lot about phonon computing. The take-home message for phonon commuting is that it will never probably be on your desktop, but you can use heat to carry and process information. And in some applications, you'd be willing to deal with the trade space to make this happen. Probably in the near future, this will help our understanding of photonic computing and be able to bridge the gap between electronic systems and photonic systems. So phononics is, in a weird way, is the bridge, even though it has probably the longest path to go before it can become that bridge. So I'll end on this because I think just as we in the first of the 21st, the 20th century brought us electronics, our ability to manipulate electrons gave us the electronic revolution. 21st century, and Dr. Pomeranke, I think, would tell me if I was wrong, the ability to manipulate photons is going to make huge advances in the technology of photonics. I don't think we're going to have to wait to the 22nd century to be able to have a technology based on phonons. So I think it's a quite exciting community to be part of. It's extremely rapidly expanding. This particular portfolio is small. It is supporting the world's leading theorist and experimentalist. We do focus on exploring these new phenomena, understanding the theoretical underpinnings, the mechanisms, and helping to guide experiments to validate some of these theories, all with the goal of enhancing the Air Force of tomorrow. And so with that, I'd be happy to take any questions. Questions, comments? Okay. Oh, no.
On this last one, what kind of information this is brand new, so you want to use a photon to carry the information in a computing sense. Do you want to speculate on that a bit?
Okay.
This reminds me a little bit of quantum computing. You know,
it is a little bit. So it turns out that the phonons have frequency modes.
Yeah.
And so by doing mode shifting, mode overlapping, just by changing the temperature, you can actually store information within those. So from what little I understand about quantum computing, and I have read and I watched the NOVA series many times, that it's very similar, but with much less efficiency and much, much slower. So.
Have you seen any kinetic theory-based model, because this explains the change in the mean free paths here?
Easy answer is no.
No, okay.
But we can talk about it offline. Okay. There is some work. Okay. So with that, I will bring to a close the power, energy, and propulsion section. And I will see everyone in the morning. Thank you for your attendance.